So again, before we actually design an experiment and go through the entire process, I want to talk to you about control, blinding, blocking, and confounding. So control, we've already talked about the importance of this, but essentially we're trying to control everything that we can. Now, sometimes in experiments, everybody goes into a treatment group. So we're comparing, for instance, people who are being treated for their peptic ulcers by gastric freezing versus another method. It could be that we now instead have a control group. So it's very possible that an entire group is controlled, which means that that group doesn't actually receive a treatment, so that we can then compare the results that way. So a control group is essentially a baseline treatment level. So what we can expect, whatever improvement we can expect based on no intervention at all. Again, the control group was no treatment, or whatever the existing treatment was, and the experimental group was the gastric freezing group. Blinding is very important because essentially it allows us to conduct an experiment and hopefully eliminate the bias that you would get if people knew that they had the correct treatment, or if doctors knew which patients had the correct treatment. So blinding is basically not allowing individuals to know which treatment group is being performed or which treatment group they are in. If it is a single blind experiment, that means only one group, either participants or evaluators, don't know who's in which group. If it's double blind, that means neither group knows which group each subject is in. This is obviously the most beneficial because, again, you're not getting a biased result from the patients, and you're not getting a biased result from the people who are analyzing the results. A placebo, I'm sure we've all heard of this, is like a fake treatment. So a placebo is a great way for control because it looks like the treatment that's being tested. And essentially the reason that they use a placebo is because sometimes just telling someone that they're being treated can make them feel better. So if you have children at home and you kiss their little boo-boos, you kissing their boo-boo doesn't actually make their boo-boo feel better, but in their mind it makes them think that yes, that's better. And that's the placebo effect. So the placebo effect is thinking that something's going to help, and therefore it does help. So placebo is a great tool to use whenever you're doing an experiment, because then you know how much of it is based on someone thinking they're going to get better, and how much of their improvement is based on the actual treatment that you're giving them. Blocking is, again, this is optional. So it's important to understand this is not necessary, but it is optional. And here's a great example of blocking. You want to test the amount of juice a lemon will produce based on the temperature it's sitting in. You decide you want to study 36 lemons, but you go to Hy-Vee, a local grocery store, and they only have 24. So then you go to Baker's, another local grocery store, Kroger for all you East Coast people, and you get another 12, but they don't look the same. They're from different shipments. The Baker's lemons look a little bit different, a little bit smaller, etc. So if I were doing this experiment, I would be concerned that the fact that I have Hy-Vee and Baker's lemons, that those are going to produce different results, and therefore they're going to skew my results. So instead, we can design an experiment using blocking that will help with those problems. So let's learn about blocking first, and then I'll show you how you would do that. So essentially, blocking is when we separate our experimental units, which is patients or lemons in this case, into groups that are not the treatment groups. So that means that I'm not going to take all of the Baker's lemons and put them in one temperature and all of the Hy-Vee lemons and put them in another temperature, because doing it that way would then show me that I don't know if the lemons from Baker's and Hy-Vee made the difference, or the temperature that they were in made the difference. So you want to make sure that it's not the same as the treatment levels, but that you are blocking based on whatever factor you're trying to eliminate the bias from. So basically it helps us clarify the difference between the treatments, and it's called a randomized block design. Another error that you need to be aware of is confounding. So let's say I taught the same course in the winter and in the spring. And in the winter, I was kind of gloomy, and so I taught in a very subdued manner, and I wasn't very enthusiastic. and I was sort of even keeled. But in the spring, I was super animated and highly enthusiastic, and I was trying to reach my students. And at the end of my course, I asked the students how much they learned on a scale of 1 to 5. Well, my winter students averaged 2.93 and my spring 4.05. So killing it as a professor. However, was that because I taught in a different manner, or could there be other factors at play? So if I'm depressed or subdued in the winter, is it possible that many of my students also feel that way? Sure. So that would be a confounding variable. So when two factors are confounded, that's what happens when the levels of one factor are associated with the levels of another. So in the example that we just talked about, the teaching style of subdued or animated is confounded because it's associated with the weather. So they are confounded because one could have influenced the other, and that wasn't what I was measuring. What I'm measuring is how much people learn from the class. So did that depend on my teaching style, or did it depend on the weather, which happened around, that could be confounded within the teaching style? So here's another example. A bank set out 50,000 low rate, no fee offers and 50,000 high rate with a fee offers. And there were many more responses for the low rate, no fee offers. But is that because there was low rate or because of the low fee? Or was it because it was both? We don't know. So instead, you could unconfound them by sending out 4 different types. So then you could specify, is it the low rate or the low fee that people are excited about? And the last, I just want to specify the difference between lurking and confounding, because that can be a little bit confusing for people. And then in our next video, we're actually going to design an experiment and kind of pull everything together. So lurking versus confounding. A lurking variable is associated with both x and y and makes it appear as though x caused y. So recall our example where we had more TVs and a longer life expectancy. So did more TVs cause people to live longer? Probably not, but they both were increased by the lurking variable of wealth. A confounding variable affects the response variable, only the response, and we can't tell if the cause was the factor, so what we changed in the experiment, or was it the confounding variable. And that's what we just talked about a moment ago with teaching style and weather.